Okay, everything works, so we can start our lecture. Let me recall that the last time we discussed the energy spectrum of harmonic oscillator, and with the help of later operators, we find that the only admissible energy levels for a simple harmonic oscillator are given by the following magic numbers. En equals n plus 1/2 h bar omega, where level n can run 0, 1, 2, and so on. All the natural numbers. So this energy spectrum is noteworthy, at least for three reasons. First, as we see, the energy spectrum for a simple harmonic oscillator is discrete. So the energy of the harmonic oscillator can take only special values. So the spectrum is discrete. Purely discrete. Second, the energy levels are equally spaced, evenly spaced. That means that the distance between nearby energy levels is fixed. So equally spaced. So the difference is given by a fixed value, the quantum of energy, h bar omega. And third, the energy spectrum, as seen, is bounded below, and the lowest possible value of energy is non-negative. It is given by I minimum, which is equal to h bar omega over 2, and this value is strictly positive. So in some sense, quantum harmonic oscillator can't be at rest. It has to bounce all the way. In contrast to classical harmonic oscillator. For classical harmonic oscillator, the ground state is a state with zero energy, where it stays at rest. And to derive the energy spectrum for harmonic oscillator, we made, I hope you remember, we made the only assumption that there is at least one eigenvalue E belonging to the discrete part of spectrum. Actually, this assumption is equivalent amounts to the existence of the ground state, that is, state with a minimum energy. And this ground state is equivalently defined by requiring that it is annihilated by the lowering operator A hat. By the lowering operator A hat. Let me show that the ground state does really exist for harmonic oscillator and is unique. And to prove this statement, it is convenient to pass to the coordinate representation. Let me recall that in the coordinate representation, the operator of the position operator is given by multiplication operator, is given by multiplication by the coordinate, and the momentum operator is given by the derivative with respect to the coordinate q. Accordingly, our later operator in the coordinate representation takes the following form: I over square root of 2m h bar omega h bar d by dq plus m omega q, and similar expression for a dagger Raison operator. Actually, it can be obtained by Hermitian conjugation of this one, so we get to m omega h bar h bar d by dq, this time minus m omega q, m omega q. In this coordinate representation, the ground state node is described as given by some wave function, psi node, which by definition is annihilated by the operator A hat. So let's show that this equation has a unique solution. Now, applying the operator A, we can ignore the prefactor, the square root, and so on. We get the following differential equation, ordinary differential equation for the function psi naught. Plus m omega q psi naught is equal to 0. Very simple differential equation, and I think everybody can solve it by separation of variables. By separation, so I can just write down the answer, the solution. The solution is given by some integration constant c times exponential function minus m omega q squared over 2 h bar. If you don't trust me, just check for yourself that this function does satisfy this differential equation. And so we see that the solution is given by the Gaussian function. And Gaussian function is obviously square integrable. So this eigenfunction indeed belongs to the distance spectrum of eigenfunctions. We can fix this integration constant c partially by imposing normalization condition. Let us compute the norm psi naught. This is given by integral over real line dq psi naught modulo square, and substituting Gaussian we get modulus of c squared times integral exponential function of minus m omega q squared h bar without 2 because of square. Okay, we can slightly simplify this integral by changing variables. Let me introduce new variable x to be q times omega, m omega over h bar. Contrary to q, x is dimensionless quantity, and our integral takes the following form: c squared. Square root of h bar m omega minus infinity x to the minus x squared dx. So I get the standard Poisson integral, and this is integral is well known. It is given by its value is square root of pi. So I end up with c squared times square root of h bar pi m omega. So to normalize my ground state function psi naught, I can take c to be the square root of h bar pi omega over omega m. So finally, I can take as a ground state the following wave function: the first square root of m omega over pi h bar times exponential function of m omega q squared over 2 h bar over 2 2h bar. Okay. Now to write down the functions, wave functions of excited state belonging to the other values of energy. I can just apply the raised operators to this function psi naught. And with the count of normalization factor, I find that the wave function for nth eigenfunction and nth eigenstate is given by 1 over square root to mh omega to the n factorial times the 4 square root of m omega over ph bar and the action of the raised operator a dagger h bar d by dq minus m omega q to the n, acting on exponential minus m omega q squared over 2h bar. That's it. Now it is quite clear that applying repeatedly this first order differential operator in the round bracket, we will get the exponential factor times some polynomial of degree n. So the action of each a dagger brings us 1 degree to the polynomial, So the answer will be given by some polynomial Pn, and refers to the degree n, times the Gaussian function m omega q squared over 2h. And these polynomials Pn, they are well known in mathematics and in mathematical physics, and they are known as Hermite polynomials. Hermite polynomials. And taken together with exponential function, altogether this is called Hermite functions. Nth order Hermite function. Okay, in terms of our variable, where is x are these Hermite function can be written as nth Hermite polynomial times exponential function of x to the power x squared over 2. X squared over 2. Well, and as you should know from mathematical physics, these Hermite functions, they form a complete orthonormal basis in the space of square integrable functions on real line. So this basis of function psi n is complete. And this proves that our eigenvectors, our eigenfunctions, form a complete set of functions for harmonic oscillator, so that any pure state of harmonic oscillator can be expanded over these basis functions. Any questions? Is it clear? Please, thank you. Ask. No, there was only one sequence, starting with ground state A, applying successfully raising operator, we get a sequence of states A dagger to the n with normalization factor 1 over square root. There is no second sequence. Okay, we can apply our lowering operator to this basis vector. Okay, we can do this, but the sequence is unique. Yeah, you're right. This is the point. So, passing to coordinate representation, we show that this basis is complete. So, because in the coordinate representation, these wave functions actually, Hermite functions, they form complete basis in the space of square integrable functions on the real Riemann. So, there is no other possibility, there are no other possible eigenstates or eigenvalues. More questions? Let me also note that all these eigenfunctions for our choice of normalization constancy, they are all real functions. Hermite functions, they are real functions, so it is quite easily to draw the picture, to plot their graphs on the plane. Let me do this. For example, the ground state and first excited state. Let me plot the graph. Here is a q-axis. Makes sense to draw the graph of potential energy. It is given by parabola, right? M omega squared over 2 q squared parabola. And here the ground state, energy, h bar omega over 2, then goes 3/2 h bar omega, 5/2 h bar omega, and so on and so forth. And for the ground state, we found that the wave function is just Gaussian, just Gaussian. Just Gaussian. It looks like this. Psi naught, function psi naught. And it is not hard to see that the wave function for the first excited state, psi1, it is proportional to q, there is only to q times m omega q squared over h to h actually. So the corresponding graph looks as looks like this. It is given by anti-symmetric function, odd function of its argument. This is psi1. And as you should remember, the modulus squared of wave function gives us probability, gives the probability distribution for the coordinate. So looking at these graphs, it is easy to decide where it is most probably to find our harmonic oscillator. Okay, let me draw the energy level corresponding to the ground state. Then we get two turning points, A and minus A, and this A is actually given by the denominator in this exponential. So A is given by square root of h bar omega over omega m. These are turning points. So basically, our oscillator is localized in the vicinity of origin of size A. This is characteristic length of the region where the probability to find our oscillator is essentially different from zero, because Gaussian function decreases very rapidly, falls home very rapidly with Q. Okay. More questions, if any? No. Actually, it is a general statement that the ground state, the wave function of ground state, can never vanish. It is always there is no points where this function can be zero. It is never zero. But it is not true for the excited state. For example, the first excited state, psi 1, is 1, 0. The second excited state will have 2 zeros, and so on and so forth. But the ground state can't reach 0. We will prove this statement later in our course. Well, if there are no other questions, let me pass to the next topic, and actually main topic of our lecture, devoted to the linear rigid rotor. So let me erase. Harmonic oscillator. So the title of the next part of the next section is linear rigid rotor. Linear rigid rotor. Linear rigid rotor is another very popular physical model, and by popularity it can compete only with harmonic oscillator, and this model will play a key role in our subsequent study of central potentials, in particular hydrogen atom problem. So it is very important for you to get familiar with this system, with this quantum mechanical system. Just to refresh your mind, let me recall that in classical mechanics, a linear rigid rotor is given by two masses, say m1 and m2, that can move freely in space, staying at the same distance from each other. So they bound together, and the bound can be shrink or stretched, so it is rigid. That's hence the name, rigid rotor. And let me denote the distance between m1 and m2 by r. It is a fixed number. Well, a typical example of rigid rotor is a diatomic molecule, say a molecule of hydrogen. The molecule of hydrogen looks like looks like a dumbbell, right? Looks like a dumbbell. And as you know from classical mechanics, the dynamics of such two-body system splits in the superposition of two motion. The uniform linear motion of its center of mass, and rotary motion or rotational motion around about the center of mass. And this last motion is usually described in terms of the so-called reduced mass. Reduced mass, m is equal to m1 times m2 over m1 plus m2. Reduced mass. Well, now if we abstract ourselves from translation motion in space, pass into the reference frame related to the center of mass, then we are left only with rotational motion. And this rotational motion can be modeled by a point mass moving on the sphere of radius r. So let me write down the picture. Coordinate axis x1, x2, x3. Consider a sphere of radius r and a point mass m moving on the surface of this sphere. So effectively, if we are not interested in translation motion in space, we have a two-dimensional mechanical system, that is a system with 2 degrees of freedom, because to locate a point on the sphere we need only two numbers. For example, as a generalized coordinates, we can take polar angle or inclination angle theta, which can run 0 to pi, and the so-called azimuthal angle phi, which runs from 0 to 2 pi. From 0 to 2 pi. From practical viewpoint, it is much easier to work in terms of the Cartesian coordinates x1, x2, x3, x1, x2, x3, rather than with the angle variables theta and phi. And it is indeed possible to work out such a description of rotor in terms of Cartesian coordinates at the cost of introducing constraints, algebraic constraints on the Cartesian coordinates x1, x2, x3, and the conjugate momentum. The first constraint is obvious. Since our particle moves on sphere at each moment of time, the magnitude of its radius vector is actually fixed by the number r. So we have the following constraint that constraints. The first constraint, just x scalar product with x is equal to r squared. This constraint holds every single time of moment. Therefore, differentiating this expression with respect to time, with respect to t, we get one more constraint. X dot scalar product with x is equal to 0 because r is just constant. This equation says that the instantaneous velocity for our particle should be perpendicular to its radius vector, x dot. So whatever the trajectory of our particle on the sphere, its instantaneous velocity is perpendicular. Geometrically, this is quite clear without any computation. So, on the other hand, using the standard relationship between the instantaneous velocity and the momentum of the particle, that is, the vector of momentum is proportional to the instantaneous velocity, and proportionality coefficient is just the mass of the particle. We can rewrite these constraints in the following way. So we may expect that in the phase space, in terms of this space, the dynamics of our rotor is described by the pair of the following constraint, namely x with x is equal to r squared, the same constraint, but here we can replace x dot with p if we are going to work in terms of Hamiltonian formalism. So the linear momentum of our particle should be orthogonal, perpendicular to the radius vector. And these two constraints on phase space variables, x1, x2, x3, and p1, p2, p3 are in good agreement with the counting of degrees of freedom. Indeed, if we start with two-dimensional mechanical system on sphere, then we have four-dimensional phase space. Two generalized coordinates, say theta and phi, and to the pair of conjugate momentum. On the other hand, if we start with Cartesian coordinates with particle moving in three space, and we have three Cartesian coordinates and three conjugate momenta. So in total we have 6 independent variables, but we impose 2 constraints on them. So the number of independent variables is 4, as it should, for our system to have 4-dimensional phase space. So in the cycle we'll work in terms of Cartesian coordinates and the conjugate momenta, keeping in mind these 2 constraints on these 6 variables. Any questions? No questions. Okay. Now the rotational character of motion suggests that probably the most important, the most promising physical quantities associated to this motion are related to the components of angular momentum, because intuitively angular momentum is somehow related to rotations, right? And as we will see in a moment, this is indeed the case. Let me recall that the angular momentum is a vector physical quantity given by the cross product of their radius vector, x, position vector, and the linear momentum, p, x cross p. Angular momentum. Let us compute the magnitude of this vector. To compute magnitude, we should compute the square of the vector. This is given by m squared, m scalar product with m, or x cross p times x cross p. And with the help of simple algebra, we can rewrite this scalar product in terms of scalar products of vectors x and p. I suppose you know this formula. And we get x squared times p squared minus x scalar product with p squared. Do you agree? And now we can simplify this expression by making use of our constraints. Our constraints say that actually the second term is equal to 0. While the prefactor x squared is just constant r squared. So I end up with r squared times p squared. So we see that the angular momentum squared is actually proportional to the linear momentum squared. And the linear momentum squared in its turn is proportional to the kinetic energy of our particle. And since our particle is on the sphere, with kinetic energy is actually total energy. So we see that the total energy of the rotor is proportional to its angular momentum. So we get the following expression for the Hamiltonian, for the classical Hamiltonian for our system. P squared over 2m, p squared over 2m is equal to m squared times m squared over 2m r squared. This value m r squared in the denominator is known as a moment of inertia. Moment of inertia. Moment of inertia. Okay. Now passing to the quantum mechanical consideration of our problem, we promote the angular momentum, or more precisely, each of three components of angular momentum vector to the corresponding Hermitian operators. So I have M1, which is given by x2 times p3 minus x3 times 2, m2 x3 p1 minus x1 p3, and finally m3 p1. And applying the canonical quantization procedure, the rules of canonical quantization, I just put heads on all these dynamical variables. Luckily, there is no ambiguity in writing these expressions because these are mixing terms with positions and momentum. They correspond to different axes. They correspond to different degrees. They correspond to different degrees of freedom. So x2 commutes with p3, x3 commutes with p1, and so on. So there is no actually ambiguity in writing these expressions. And as a result, we get three Hermitian operators built out of the positions and momentum. You need to remember all these expressions by heart. It is enough to remember only the first one, where the indices 1, 2, 3 goes in natural order, because the other two expressions are obtained for this one by cyclic permutations of indices 1, 2, 3. 1, 2, 3. So it is not to remember the first expression. Moreover, all these three formulas can be given by one, can be written as one formula by a single expression with the help of the so-called Levi-Civita tensor or Levi-Civita symbol, which is usually denoted by epsilon ijk, xj hat k hat. My convention is epsilon 1, 2, 3 is equal to 1. Levi-Civita symbol is supposed to be totally anti-symmetric with respect to a permutation of indices I, j, k. So with this convention, all the other components of tensor epsilon can be restored from this one by anti-symmetry. And of course, I assume summation over repeated indices. In this case, we have repeated indices kk and jj. Now, using the canonical commutation relation for the positions and momentum, that is pi with xj is equal to ih bar Kronecker delta ij, we can deduce the following commutation relation for the components of the angular momentum. Mi with mj is equal to minus I h bar epsilon ijk mk. Again, summation over repeated index k. Actually, you have already derived these commutators on one of our seminars, so I will not dwell on this again. And you also know that these operators, M1, M2, M3, they all commute with a square of angular momentum. M squared commutes with all mi, so as they where by definition m squared is given by m1 squared plus m2 squared plus m3 squared. And let me draw your attention to the fact that angular momentum is dimensional physical quantity. It has units. So its dimension is of each of three components coincides with the dimension of the Planck constant h bar. That is joule times second. Joule times second. And in the following, it will be convenient to work in terms of dimensionless variables, dimensionless operators, and these are easy to obtain by dividing the components of angular momentum operators by the dimensional constant h bar. So instead of, for example, instead of M3, I can introduce new operator which I will call J3 as minus h bar to the minus 1 M3. And this operator is dimensionless because of this combination. And I can do the same thing with the other two components, M2 and M3, but from practical viewpoint, it is more convenient to introduce some complex linear combinations of dimensionless linear combinations of M2 and M3. I'll denote them J plus and J minus. The operator J plus is by definition minus H bar to the minus 1 and 1 plus I M2. And J minus is given by minus H bar to minus 1 and 1 minus I M2. And as a seen, the operator J3 is Hermitian because M3 is Hermitian and H is a real constant, so we get that J3 conjugate coincide with J3, while the operator J plus and J minus, they are not Hermitian, they do not correspond to any to observables, but they are adjoint to each other. They are related by Hermitian conjugation. So that is J minus adjoint is equal to J plus. And the other way around. The adjoint of J plus is J minus. Okay, any questions? No questions. Let's take a break, 5-minute break. Let us continue our lecture then. And so we have introduced the operators J as some complex linear combinations of the angular momentum components. And we can think of this replacement as a change of coordinates, linear coordinates in the space spanned by M1, M2, M3. And in this new basis, G basis, the commutation relations for the angular momentum, for the components of angular momentum, take the following form. I need more space. I think I can erase this classical part of the story. So in this new basis of operators J3, J plus, J minus, the commutation relations take the form J3 with J plus minus is equal to plus minus J plus minus, and J plus with J minus give us 2J3. That's it. And it is also possible to write the expression for the operator M squared in terms of J plus and J minus. Actually, these are M squared is proportional to H bar squared J squared, where J squared is given by 1/2 J plus J minus plus J minus J plus. Notice that operators J plus and J minus do not commute to each other, so their order does matter. Plus J3 squared. You can check this quality by direct substitution of the definitions, and it's not hard to do. And notice that with the help of this commutator, we can transpose operators J plus and J minus, and either in the first term or in the second. If we do this with the second term, interchanging J plus with J minus, we get the same term, J plus J minus, plus some additional term proportional to J3. So we can, with the help of this commutator, we can rewrite this as J plus J minus plus J3 squared plus, more precisely, minus J3. Equivalently, transposing J plus and J minus in the first term, I can write this operator as J minus times J plus plus J3 squared, and this time plus J3 hat. J3 hat. These are very useful formula, as we will see. And as you might probably guess, these operator J plus and J minus, they are analogous to the ladder operators which we have introduced for harmonic oscillator, which we use for harmonic oscillator. In so doing, the role of Hamiltonian of the harmonic oscillator will play operator J3. So they are raising and lowering operators for the eigenvalues of the operator J3. The main difference between this picture and harmonic oscillator is that now J3 is not the Hamiltonian of our system. The Hamiltonian of our system is given by J squared, not J3. So these operators J plus, J minus will increase or decrease the value of J3, but not J squared. So in a sense, this model is more involved, more complicated compared to the simple harmonic oscillator. Now, from these commutation relations, it follows immediately that the operator J squared commutes with operator J3, J plus, and J minus, because J squared is proportional to M squared, and the operator M squared commutes with all the components of angular momentum and their linear combinations. So we can write that commutator J squared with J3 is equal to 0, and the same true for J squared with J plus minus 0. From the first equality, we conclude that the operators J3 and J squared, being Hermitian operators commuting to each other, they can be included to some complete set of observables. So, being Hermitian and commuting, they can be included to some complete set of observables. I don't say that they form complete set of observables. I don't know. At the moment, we don't know whether they form complete set or not. But anyway, they can be included in some maybe more extended set of observables. By the end of the day, we will see that they do constitute a complete set of observables. Okay, and since these operators commute to each other, we can find their common, we can speak about their common eigenvectors. Let EM be one of such common eigenvectors. That is, applying operator J squared, I get the eigenvalue E times EM, and applying the operator J3 to the same state vector, I get the eigenvalue M. So these labels E and M refer to the eigenvalues for the operator G squared and J J3. Let me also suppose that this the norm of this eigenvalue is 1, so this state is normalizable. Again, this is my assumption. And the problem now is to identify the possible spectra of eigenvalues E and M. What are possible eigenvalues for the operator G squared and J3 squared? We will solve this algebraic eigenvector problem by algebraic method. That is, by making use the commutation relation for the angular momentum operator. Or it is the same for the operators J3, J plus, and J minus. And the first thing to do is to decide which values can take the eigenvalue M for a fixed value E. By the way, I use letter E to denote the eigenvalue of J squared deliberately to emphasize that this operator J squared is proportional to the M squared and hence to the Hamiltonian of our rigid rotor. So finding the spectrum of operator J squared is equivalent amounts to finding the energy spectrum. So let us fix the energy and decide which value may take the M for a given E. And to answer this question, I will do some little mathematical trick. Actually, it is quite similar to what we did for harmonic oscillator. Let me make the following sandwich of operators J minus J plus plus J minus in between ket E M and bra vector M E. Let me also put 1/2 in front of this expression. As you can see, this operator in between is actually a part of the definition of the operator G squared, right? Exactly this term, G squared. So I can rewrite this expression as follows. This is EM, and instead of this bracket I write G squared minus or plus minus G3 squared. Do you agree? This is just from the definition of G squared. But the eigenvector EM was chosen to be the eigenvector was chosen to be eigenvector for the operator G squared and G3. So I can apply this operator immediately to this ket vector to get E minus M squared. E minus M squared. Now let me introduce some auxiliary ket vectors, psi plus minus, given by J plus minus on EM. Then the corresponding bra vector, psi plus minus, is given by m times g minus plus. Hermitian conjugation replaces plus with minus and vice versa. So, and I see that in terms of these vectors psi plus minus, I can rewrite this original expression in this way. This is just 1/2 psi plus plus 1/2 psi minus psi minus. Is it clear? So I apply this operator on the left, this on the right, this on the left, this on the right, and this gives me psi plus, this gives me psi minus. And it is quite clear that these quantities can't be negative because they express the length of the vector. This equals to or greater than 0. And this difference is greater to or equal to 0, 2. So I get the inequality from inequality E is greater than or equal to m squared. Actually, this inequality has a very clear geometrical explanation. Very clear geometrical explanation. What is E? E is eigenvalue of the magnitude squared of some vector. And what is m? M is the length of its projection. So what this inequality tells us is actually that the magnitude of projection can't exceed the magnitude of the vector. Can't exceed the magnitude of the vector. Is it clear? Thanks. Okay, let's move ahead. And okay, now starting with this eigenvector M, we can construct more eigenvectors for common eigenvectors for our operator G squared and J squared and J3. For instance, let me check the vectors psi plus psi minus. I claim that these vectors are both eigenvectors of the operator J squared. Why? It is very easy actually, because operator J squared commutes with all operators J plus, J minus, J3. So applying this operator J squared to psi plus minus, I actually act to the J plus minus on En. Now I can transpose these operators here because they commute to each other and get J plus minus J squared En, and since this vector is eigenvector of J squared, I get E J plus En, that is So I see that both these vectors, psi plus and psi minus, they are eigenvectors. The eigenvectors of our operator G squared with the same eigenvalue E. So action of the operator J plus J minus on our vector EM doesn't change the eigenvalue E. Moreover, it turns out that these vectors, psi plus and psi minus, are also eigenvectors of the operator J3. Let us check. Again, at this point we can use the commutation relations for the operator up here, and interchanging the operators we get J plus minus J3 plus minus J plus minus on EM. Again, applying the operator J3 to our eigenvector, we get the eigenvalue M. So we end up with M plus minus 1 psi plus minus. So I see that the vectors psi plus minus are eigenvectors for J3 with eigenvalues M plus 1 or minus 1, depending on the sign. So whenever the vectors psi plus minus are different from 0, when they are non-zero, they are eigenvectors for the pair of operator J squared and J3. Now, applying the operator J plus, J minus successively to our eigenvector EM, we can build a sequence of eigenvectors EM, J plus, EM, J plus, squared, EM, and so on. And the same for J minus. So J minus, EM, J minus squared, EM, so on and so forth. Obviously, this sequence can't go indefinitely to the right and to the left, because actually of this inequality. As I have told you, this eigenvector has eigenvalue m with respect to the operator J3. This has eigenvalue m plus 1, m plus 2, and so on. You have m minus 1, m minus 2, and so on. So each time when I apply either operator J plus or J minus, I increase or decrease the eigenvalue by 1. So the absolute value of m always decreases. But we have an upper bound for m squared. And this implies that there must exist some highest and lowest vectors in this sequence. Some highest vector em2 with a maximum possible value of m, and the lowest vector em1 with the minimum possible value of m. And these two extreme vectors, highest and lowest, satisfies the following equation. By definition, the highest vector should be annihilated, is annihilated by operator J plus. So applying J plus, I don't get an eigenvector with eigenvalue m2 plus 1. I get just 0. And the same is true for vector m1. Applying J minus, I get 0 again. So the defining property of this eigenvector is that J minus on E m1 is 0 and J plus on E m2 is 0. And these equations are very useful. As we will see, these equations allows us to identify the possible values of m and the possible values of energy E. And to do this, let us apply the operator G squared to the lowest vector em1. And to do this, we can use one of our two. Okay. We can use one of our two representations for the operator. G squared. Okay. Which one? This or this? What do you think? Right. That's right. Because why right? You see, this lowest vector is annihilated by J minus. So it makes sense to use this one. Because this term, the first term, will give us 0, just 0. And then we are left with two terms, J3 squared minus J3. So we're using the first representation for J squared. And the fact that vector em1 is annihilated by J minus, we can write this as J3 squared minus J3 em1. And since em1 is an eigenvalue vector of J3, we get immediately m1 times m1 minus 1 E m1. And in similar way, we can apply J squared to the highest vector, em2. This time we can use the second representation, where J plus goes first and annihilates our eigenvector. So again, we are left with the last two terms. So we can write J3 squared plus J3 on E m2 and end up with m2 plus 1 E m2. But on the other hand, both these eigenvectors belongs to the same eigenvalue of the operator j squared. What is this eigenvalue? Who can answer? Who knows the answer? What is eigenvalue? By definition, this is E. E is eigenvalue of the operator j squared. So here we have E, E, M1. Here we have E, E, M2. So these two eigenvalues, both these eigenvalues, M1 times M1 minus 1, M2 times M2, they are equal. They are equal to E. So we can equate them. So in such a way we get the following equality. M1 minus 1 is equal to M2 times M2 plus 1. And after some simple algebra, we can transform this equality into the following one: M2 minus M1 times M2 minus M1 plus 1 is equal to 0. So these equations are equivalent to each other. Notice that the second bracket can never be 0. Can never be 0. Why? Because by definition M2 is greater than or equal to what? M2 is greater than or equal to M1. So by definition M2 is equal to or greater than M1. So this bracket is certainly non-zero. So the equality is only possible when M2 is equal to minus M1. To minus M1. Okay. What about this number? M2 minus M1 plus 1. Let us compute the number of eigenvectors in our sequence from the lowest to the highest. How many terms in this sequence? Who knows? Please, compute. The eigenvalue m is going with step 1. M plus 1, m plus 2, up to m2. M minus 1, minus 2, up to m1. So, how many terms do I have in this sequence? Y2. M2 minus M1 plus 1. So the number of terms is equal to M2 minus M1 plus 1. And with the count of this equality, we can write this as 2m2 plus 1. And by definition, this is an integer number. It's a natural number. So we conclude that the eigenvalue, the highest eigenvalue for the operator J3 should be either integer or half integer. This is a very important number, so let me introduce a special notation for it. In the following, I will denote it by j. J is m2, or what is the same, minus m1. And according to our computations, this j may take only integer or half integer values. 0, 1/2, 1, 3/2, and so on. And so okay, is it clear? M2 plus 1. What's wrong with this equation? I see. Thank you. You're right, quite right. Plus, not minus. Okay, thank you. So let us summarize where we have got to. So starting from some common eigenvector, En, summary. En, we have constructed a sequence of common eigenvectors with n taken values from minus j to j with step 1, minus j plus 1, minus j plus 2, up to j minus 1, j. And we know that this number j should be either integer or half integer. Moreover, it follows from our computations, actually, that the eigenvalue E is related to this j by this way. So we see that the eigenvalue is not arbitrary. It is given by j plus 1. And this is a culminating point of our discussion. We see that the energy of the linear rigid rotor is quantized. It can take only some discrete values labeled by integer or half integer j. Now, it is quite clear that these vectors En, they form orthogonal system because they belong to different eigenvalues of Hermitian operators. Upon normalization, they give us some orthonormal set of vectors. I will denote the elements of this orthonormal basis by by Jn. So instead of E in the cycle, I will be use the letter J related to E by this formula. So upon normalization, I may assume that these vectors satisfy the following relation: Jm with J prime m prime is equal to delta m prime, delta j prime. So they form orthonormal bases. And I know that all these basis vectors are eigenvectors for the operator j squared with eigenvalue j plus 1 times jm and the operator j3. Of course, these are also with normalization condition. Do not fix our basis completely because we have inevitable phase ambiguity. We can always replace any basis vector gm with a new multiplied by an arbitrary phase factor phi jm. So what remains to do is to work out explicit formulas for the action of the operators j plus minus on our basis vector j and m. We know how to act by operator j3, but we don't know how to act by operator j plus and j minus. We know that these operators increase or decrease the eigenvalue m by 1, but we can ensure that the resulting vector has not 1. So it will be some vector proportional to the nearby vector. So there must be some complex constant j m plus minus 1. So our next task is to identify these complex numbers c, j, m. And we will do this at the next lecture. On Saturday. And that's all for now. If you have any questions, please ask. No questions? Okay, then I stop recording. Thank you for your attention.